This presentation introduces interactive proof systems within the theory of computation. We will explore the concept of interactive proof denoted as IP, Arthur-Merlin protocols denoted as AM, and their relation to various complexity classes. An interactive proof is defined as a protocol, which is a series of interactions between two parties, a prover and a verifier. The purpose of this protocol is to convince the verifier of the truthfulness of a particular statement. Key properties of interactive proofs include completeness, ensuring that true statements are always accepted, and soundness, which ensures that false statements are always rejected. In an interactive proof system, there are two distinct entities, the prover and the verifier. The prover is computationally unbounded, meaning it has virtually unlimited computational resources. Its goal is to convince the verifier of a certain statement. The prover has unlimited power but may potentially be dishonest. On the other hand, the verifier runs in polynomial time, indicating it has limited computational power. It needs to be convinced by the prover and is always honest. The complexity class IP encompasses languages that possess polynomial round interactive proof systems. These systems involve a polynomial number of rounds of interaction, a probabilistic verifier that uses randomness, and two-way communication between the prover and the verifier. The structure of an IP protocol involves several steps. First, the verifier sends a random challenge to the prover. Then the prover responds with an answer based on this challenge. These steps are repeated for a polynomial number of rounds. Finally, after these interactions, the verifier makes a final decision to either accept or reject the statement. Arthur-Merlin Games, denoted as AM, involve two players, Arthur, who represents the verifier, and Merlin, who represents the prover. Arthur makes public coin flips, meaning that his random choices are visible to Merlin. Merlin, upon seeing all the randomness, responds accordingly. The key difference between Arthur-Merlin Games and interactive proofs is that the verifier's random choices are public rather than private. The Arthur-Merlin complexity classes can be arranged into a hierarchy. At the base is the class MA, where Merlin sends a proof and Arthur verifies it in one round. Above that is the class AM, where Arthur challenges and Merlin responds in 2 rounds. This hierarchy represents the increasing complexity of interaction between the two parties. The complexity classes related to interactive proofs have certain inclusion relationships. NP is a subset of MA, which in turn is a subset of AM, and AM is a subset of IP. A famous result in this area, known as Shamir's theorem, establishes that IP is equal to PSPACE. Let's consider the graph non-isomorphism problem, or GNI, where given two graphs G subscript 0 and G subscript 1, the task is to prove that they are not isomorphic, meaning they have different structures. An interactive protocol to demonstrate this involves the verifier, denoted by V, picking a random I from the set 0, 1. The verifier then sends a permuted version of G subscript I. The prover, denoted by P, then identifies which graph it is. This process is repeated to reduce the error. Interactive proof systems have numerous applications and hold significant importance in the field of computer science. They are used in zero-knowledge proofs, cryptography, blockchain verification, and privacy protocols. They have expanded the notion of what constitutes a proof, utilize randomness as a valuable resource, form the foundation for modern cryptography, and bridge the gap between theoretical concepts and practical applications. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.